We will take another problem. In this problem, it will be illustrated how a design engineer uses the module for selecting the gears. So in this problem, it is provided that the gear ratio needed by the designer is 10 raised to 1 to 10 to 1. And it is known that the distance between centers of the gears is equal to 660 mm. So with this data, this will be usually the design data available to the designer. We want a gear reduction in some machinery and we know that between shafts how much distance is permissible. With that we have to design a gear. So some constraints are put there. First constraint is that given the gears are of standard profile, that is in standard profile the addendum is equal to module and the pressure angle is also given. Case 22.5 degree is given for the pressure angle for the designer. With that we have to design the gear. So we have to find first part of the problem, find one module for no interference to occur. In this case, if you have noticed, the module was not given. We have to calculate a module first. And the second part, number of teeth on each wheel, on each gear. So we'll go ahead with the solution. So module is determined by the condition that no interference should occur. So for that, no interference, the maximum addendum radius should be equal to r square plus 2r small r sine square xi plus r square sine square xi. This you can recall from our derivation on the interference. In that section you will find the complete derivation. This is the maximum permissible addendum for the wheel. Max wheel addendum circle radius. We have to calculate r, small r, xi is given. So we will use the our given quantities, that the gear ratio is 10 raised to 1 and the distance between center is 660 mm. So O1 to O2 is 660 and there is a point P which divides the P circle, the central lines in a ratio of 1 raised to 10. So you get a reduction ratio of 10. From this diagram we have a small r and big R. The small r plus big R is equal to 660 mm and small r by big R is the reduction ratio that is given as 1 raised to 10. So if you simplify these two solutions, you get r equal to 60 mm and capital R is equal to 600 mm. Now we can go ahead on calculating RA. So RA will be, maximum value of RA will be R square, so 600 square plus 2 into 600 into 60 into sine plus 60 sine square 22.5. If you simplify this expression, you will get RA is equal to 609.1 mm. Now RA, the radius of addendum circle is equal to the radius of this circle plus the addendum. So hence addendum will be equal to RA minus R 09.1 minus 600. We have derived for the wheel because the limiting case for the interference is wheel, and hence addendum is 9.1 mm. Now it is given that the teeth is standard, so hence module is equal to addendum. So hence module is equal to 9.1 mm. So here find the module of the gears. That is same for both the pinion and the wheel, and this is answer for the first part. Now for the second part, number of teeth are asked. This is now pretty much straightforward once you know the module. So you know that module is equal to diameter divided by number of teeth. So diameter is equal to 2 into r, the radius of the pitch circle of the wheel, divided by t. So 2 into 600 divided by number of teeth that has to be determined, and module we know as 9.1. Okay. To simplify this thing, we get t nearly 133.1. So for taking the whole number just below this thing, the teeth on wheel are t is equal to 133 teeth. So if you take 133 teeth on the wheel, then teeth on pinion will be equal to the reduction ratio is equal to 1 by 10. That will be equal to number of teeth on the pinion divided by number of teeth on the wheel. So T will be T by 10. That will be 133 by 10. This is 13.3. So again, 0.3 teeth is not possible. We have to choose a number which is a whole number for both the wheel and the pinion. So we'll choose the nearest one for that. The number of teeth we'll try to choose lesser only, not more, for simplicity. So we'll choose capital T is equal to 130 and small t is equal to 13. So this selection also you have to do on your own, and this is the answer for the second part. So in this example, we have seen that just by knowing the gear reduction ratio, which is a very preliminary requirement, and the distance between the shaft, and using the standard convention, we have determined the number of teeth on the gear and pinion, and also the module. So we can do the gear design like this. You can choose the correct gear, and if you know the correct module and number of teeth, these things can be purchased. Now we will take up another problem that will illustrate the concept of forces on gear train, how the forces are transmitted. So this is wheel, this is pinion. The number of teeth on the wheel are given as 40, and the module is also given. Module is same for both the pinion and the wheel, is 6.5 mm, and it is told that the wheel transmits 4 kilowatt of power at 360 rpm. The first question asked is that find the force on wheel shafts, so the reaction on wheel shaft, ignoring any friction, just from the transmission of the motion through the gears. So ignoring any friction or other forces, just by what is the load on the bearings of the shaft. This is the step in the calculation of gear design. And the second question is asked is that what is base circle diameter of wheel? So we'll take up one by one. For the first part, we have to find the force. So we know that power is equal to torque into omega. So that we need to know omega. Omega is equal to 2 pi into number of revolution, that is 368 rpm. So this is equal to 12 pi radian per second. And power is given as 4 kilowatts. So 4000 is equal to torque into 12 pi. So torque is, if you simplify, you get around 106.2 Newton meter. Now the torque is given as force into radius. Now if you consider the gear profile, the engagement, there is a pressure line which is at an angle to the common tangent for the fixed circles. So now for the torque point of view, you need the force along the common tangent. You don't need the force along the pressure line. You need the force along the common tangent. And this is R, the fixed circle radius of the wheel, and force along the common tangent we calculate from this formula. So F along tangent will be torque divided by R. So R is capital in the case of wheel. For this we need R. So R can be determined from module, since module is equal to d by t. So 2R is equal to m into number of teeth divided by 2. So module is given as 6.5 and the number of teeth is 40 divided by 2. So R is equal to 130 mm. But we have here the torque in Newton meters. So we'll take R in meter. So torque is 106.2 Newton meter and radius is 0.13 meter. Force, tangential force at the pitch circle is coming around 816 Newton. Now if you see the tangential force, this is tangential force and this is a pressure line. So actual engagement between the gear happens at the pressure line. So let's say if Fp is a force, Fp is normal force at gear tooth, and pressure lines makes an angle xi with respect to the common normal tangent to the base circle at the pitch point. So Ft will be equal to Fp cos xi, because Fp, the normal force pressure between the meeting point, is the originator of the pressure transmission. Only a component of that which is perpendicular to the pitch point is determined, is helping in torque transmission. So Fp will be equal to Ft by cos xi is equal to 816 by cos 20 degree, the xi was given 20 degree is equal to 869 Newton. So shaft thrust will be equal to 869 Newton. This is answer for the first part. Second part, it is asked that the base circle of the wheel, base circle diameter of the wheel that is required for the involute profile generation. So we know that the geometry here, this is a fixed circle, then you have the central point, and then there is a concave circle, a line is passing for the force line, you drop perpendicular on the force line, and then you get the base circle. Okay. So this distance O2, I2 is the base circle radius. So O2 and this angle is I, the angle between the common tangent and the pressure line. So this is a pitch point. So O2P cos xi is O2I2. O2P cos xi, and O2P is radius of the pitch circle diameter R cos xi. So xi is 120 degree in this case. The radius is 130 mm into cos 20. Calculate the value 122.5 mm. Base circle radius, and base circle diameter is 2 into radius, which is 122.5 around 245 mm. This is the answer for the second part. Before concluding the section of gear theory, I'll make one final note on problems related to the distance between center of shafts. So this distance in actual practice in operation due to shaft misalignment, this d can vary. So what is the effect on gear parameters due to the d variation? So if you zoom in the tooth profile, here is your tooth and here is another tooth. So if the distance between the centers are changing, the tooth will be less engaged with each other. So that's why the effective addendum radius will reduce. Effective addendum radius and consequently effective addendum will reduce. So hence the working depth will reduce. And you know that the path of contact is primarily dependent on the addendum. When the addendum cuts the pressure line, the line of action, that place. So if the addendum radius is reducing, it will cut at a very early point. So path of contact will reduce, when the gear D increases, spacing between the shaft D, when it increases, you get these effects. Effective addendum will reduce, working depth will reduce, path contact will reduce. Final thing, two teeth are in mesh with each other. They are designed to touch on the other side. So when the centers move apart, this profile comes like this. So it is out of the profile and the backlash so increases. It is clearance between the adjacent teeth. Now we move on to the second topic in the chapter of gears, that is gear trains. A gear train is defined as the combination of gear wheels. So if you see the structure of a gear, you can see that when one gear is engaging with the another, still there is scope for that second gear to engage with the third one. And similarly, the third one can engage the fourth and so on. So like that, if you are arranging various gears in a form of a chain, and the shaft position can be anywhere, and they can be another gear here, and can be driving another gear here. So the position can be anywhere. Such kind of combination are called gear wheels. They are arranged in such a fashion that to achieve a desired velocity ratio from input to output and placement of shafts. So sometimes with a single gear arrangement, it is not possible to place the shaft in the required fashion. You need to do some transmission through 2-3 gear trains, and sometimes the velocity ratio is also not achievable a single gear train. Let's say if you want a very high reduction, you use one gear train, and then you use further smaller on the second one. So in that way, you can get large velocity ratio reduction. If you want to do a simple system of two gear wheels in some specialized application, the design may come out such that the radius of one wheel is too high, or the tooth spacing is too much, or the load on the gear is so high that it is out of design limits. So in that case, you have to break the problem into small parts and form a gear train. So our task is to determine the transmission of velocity from input to output. So let's say one of the gear in the gear train will be input, another gear will be output. It can be anyone according to the functions desired. First, we will consider the case of simple gear train. The simple gear train is nothing but what is shown in the figure above. It is a collection of gears. So for start, we will just consider the case of 3 gears, and the same thing applies for the larger subset also. So let's say that this is the input gear. Let's say the gear name is A. Then there is an intermediate gear, that name is B, and then there is an output gear, that is the name is C. So the first condition, necessary condition for transmission of motion through the gear train is that the teeth on all gear train should be same. This means that the pitch of the teeth, in the case of the gears, we have the circular pitch of teeth should be same. So then, if this condition is satisfied, then movement of one teeth on A will result in movement of one teeth in B, and similarly movement of one teeth on B will result in movement of one teeth of C. So continuous motion transfer will happen. If this condition is not satisfied, if the teeth pitch is not same, they may rotate for a particular arc, but then the gear will get stuck. So this is the condition for continuous motion transfer. The circular pitch should be same. So the circular pitch is defined as pi d divided by the number of teeth on any gear. This should be same for all the 3 gears. In simpler terms, the pi is anyway constant, so d by t, that is the module of all teeth should be same, and the other key quantities such as addendum and dedendum are also defined in terms of module, as we saw in the earlier lecture where we discussed the standard proportion. So the module for all the these should be same. So module equal to, let's say for the gear A, it will be dA by dA, number of teeth on A will be equal to diameter of B divided by number of teeth of gear B equal to diameter of teeth C divided by number of teeth of gear C. So here D is the pitch circle diameter for each ABC. So DI will be the pitch circle diameter for the IF gear, and T is number of teeth. So now we will derive the transmission ratio and the velocity ratio for the gear chain. So for the gear chain, you know that at the point of engagement of teeth between the gear A and B, the velocity of transmission should be same. So velocity at any point on the fixed circle diameter, fixed circle velocities for all gears should be same for condition of no slipping. So we earlier defined the fixed circle as the circle of which diameter we can replace a gear train by rollers, and when the rollers are touching each other, they will transfer the motion without any slipping. So that is the definition. So that means the velocity on the surfaces of all these three circles, which are the three circle of gears A, B, C respectively. So it says this is VB and velocity is VC. So at the common point of contact, the velocities will be same. So hence VB in this direction. So VA is equal to VB here, and at this point we see that VB is equal to VC. So VA is equal to VC is equal to VC. The circle velocities. Now we can calculate the circle velocities. Let's say if the gear A is rotating at an angular speed of omega A, then B will be rotating at an angular speed of omega B, and C will be rotating at an angular speed of omega C. You can see that the direction reversal takes place for direction reversal of the angular velocity takes place for each gear pair. So if you want the same direction sense also, you need a gear train. It is also another application of the gear train. So the A and C input and output shafts are rotating in the same sense, clockwise, while B is rotating anti-clockwise. So direction reversal is also one property. So if you're just taking the absolute value, then VA will be equal to omega A multiplied by dA by 2. So D is the, just to describe the fixed circle diameter, divided by 2 will be the fixed circle radius. Fixed circle radius, it is RA, which is RB, and this is RC. So RA is equal to dA by 2. This is RA. And similarly, VB will be omega B into dA by 2, and omega, and similarly VC will be omega C dC by 2. So these three quantities are equal, VB, VC. So hence omega A dA, casting out the 2 as a common term, is equal to omega B dB is equal to omega C dC. So this is one condition. So hence we can determine from input to output directly we can correlate between these two without going to details of the intermediate gears. So if you know the pitch circle diameter of the output and pitch circle diameter of the input, you can calculate the velocity ratio. So velocity ratio is defined as speed of driver divided by speed of driven. So this thing you should remember that the driver is at top and driven is at in the denominator. So driver here in this case is A, gear A, so omega A by driven is omega C, the gear C. And this thing from this identity, from this equation, omega A by omega C will be dC by dA. This will be equal to dC by dA. Now from the condition of constant modulus that we saw earlier, that modulus which is equal to d by t is constant. So hence d A by TA is equal to dC by TC. This will be equal to dB by TB also. So we are just considering the input and output here. So hence dC by dA will be equal to TC by TA. So this quantity omega A by omega C will be equal to TC by TA. So this angular speed of A can be expressed as 2 pi NA. NA is the rotational speed in RPM divided by 60. Omega A is equal to 2 pi NA. Similarly, omega C is equal to 2 pi NC by 60. NC in RPM. So if you substitute these values here, 2 pi by 60 is a common term that will get cancelled, and we'll get NA or velocity ratio is equal to NA RPM of input divided by RPM of output, that is NC. This will be equal to TC by TA, number of teeth at the output gear divided by number of teeth at the input gear. So this is a definition we should remember, and we should remember that the velocity of driver is at numerator, and when you call number of teeth, the velocity of the number of teeth of the driven gear is in numerator. Another quantity of interest defined in the velocity transmission is the train value. So train value is nothing but inverse of the velocity ratio. So the velocity ratio is defined as out driver speed by driven speed, and so train value will be reciprocal to the driven divided by driver, the speeds of that. So driven is C, so omega C is NC by NA is equal to TA by TB. Now another important definition for the gear trains is the load transmission or gain or transmission of a gear train. This is also similar to the mechanical advantage that we have defined earlier in the chapter 1 on mechanism, mechanical advantage, MA. So it is given as a ratio of load to effort. For per unit effort we are spending, how much load we are able to bear. So that means the output force or output torque in the case of gear divided by input torque or input force. So let's say tau is the term used for torque. So output torque is on the gear C. So tau C by tau A. Now from the power, earlier also we derived the equation for the mechanical advantage. For that you don't need to, it is same as a gear or transmission of forces in a gear train or any mechanism. We don't have to do a detailed derivation of torques. We know from energy conservation, power conservation, that power is equal to torque into angular velocity. So power is equal to tau into omega. So for no loss system, no friction loss or no other loss, we get input power equal to output power. So input power will be tau A input torque into input angular velocity, which will be equal to output torque into output angular velocity. So from this we get tau C by tau A is equal to omega A by omega C. So hence the ideal mechanical advantage, that is the mechanical advantage without any losses, will be equal to tau C by tau A is equal to omega A by omega C, and this we know from the our definition of velocity ratio, that the velocity ratio is driver speed by driven speed, so omega A by omega C. So this value is same as the velocity ratio. So the ideal mechanical advantage is equal to velocity ratio, and that is equal to Tc by Ta for the case of gear, number of teeth at the output gear divided by number of teeth at the input gear. In case effect of friction has to be taken into account, then real mechanical advantage will be equal to efficiency of the system multiplied by ideal mechanical advantage. So ideal mechanical advantage is equal to, it just can get from the gear ratio Tc by Ta. Real mechanical advantage, if the efficiency is known, you can get the real mechanical advantage. Otherwise, if real mechanical advantage is given as a ratio of torque, the real torque at C divided by real torque at A, all these real values, then you can calculate, you will substitute the value tau C by tau A, and you can calculate eta. So either way the numerical can come.